we are going to look at proofs according to P2 and Excel, whereby we're going to look at proof by exhaustion. We shall look at proof by counter examples. So the first kind of questions that you may be tested is a question like this. You are told that a student was asked to prove by exhaustion that if an integer, n is an integer, then n squared, we are having n squared plus n plus 1 is not divisible by 3 if n is an integer. The student started the proof by showing n is equals to 3k and then went ahead like that. Now, if you are that student, how can you be able to perform that particular proof? What are you supposed to do in order to prove that? So something that you need to remember here is one thing. You need to remember that an integer is a positive or negative number. So which means that it can either be an odd number or an even number. So we are going to start with let n be equals to 3k plus 1. That is the first one we are going to start by showing. And in this case, you can see here, let me just have a bigger space where we can be able to write. We want to show that 2n squared plus n plus 1 is not divisible by 3. How do you prove that? Now, the way to prove that, we are going to let n be equals to (3k plus 1). Then we are going to substitute that into this equation that we are given. So we shall have 2 into 3k plus 1 squared plus 3k plus 1. Then we shall have plus 1. So we have now substituted this 3k plus 1 into that particular equation that you are given. If we expand this, what are we going to have? We shall have 2 into this squared is going to be 9k squared plus the shortcuts to expand this, square this number, you get 9k squared, multiply this term and the second term, you get 3k times 2, that becomes 6k, then plus 1 squared, which is actually 1, plus 3k plus 1 plus 1. So if we open the bracket, what are we going to have? You are going to have 18k squared plus 12k plus 2 plus 3k plus 2. So if you add this one, we're going to get 18k squared plus 15k, then plus 4. So which means that this equation that we have here can be written as 18k squared plus 15k plus 3 plus 1. So this part that we have, we can be able to write it in terms of as a factor of 3. So 3 will be 6k squared plus 5k plus 1 plus 1. So you realize that whatever that we are having here, whatever part that we are having here is 1 more than the multiple of 3. So which means that this one here is not divisible by 3. It's not divisible by 3. Yeah. So whatever we have here is not divisible by 3. because it's 1 more than the multiple of 3, so it's not divisible by 3. Then we can also try, now we worked out that, we can also say let n is equals to 3k plus 2 now. 3k plus 2 or 3k minus 1. If we substitute it here, we are going to have 2 into 3k plus 2 squared plus 3k plus 2 plus 1. So if you expand this, what are you going to have? This is going to be 2 into bracket 9k squared plus 12k. Yeah. Okay. Then this squared is going to be 4. Then plus 3k plus 3. This and this. Then if we open the brackets, we shall have 18k squared plus 24k plus 8 plus 3k plus 3. So if I want to put this together, I can say it's 18k squared plus 27k plus, so I can say this is going to be 9 plus 2. So also on this case, you can realize if I can rewrite this, I can say this is equals to what? This is going to be equals to, I factor out 3, is going to be 3 into 6k squared plus 9k plus 1 plus 2. So you realize also this one is 2 more than the multiple of 3. Then it also is not divisible. So if you have looked at this, when you have an even number and when you have an odd number, then it means in both cases, and we have confirmed or we have proven that not divisible by 3, not divisible by 3. So we can be able to say, hence 2n squared plus n plus 1 is not divisible by 3, because we have proven here is not divisible by 3 and also here is not divisible by 3, and then we have exhausted, because for an integer we have even numbers and odd numbers. Both of them we have tried, we have put there, and we have confirmed they are not divisible by 3. Then it means that this expression you are given is not divisible by 3. So let's look at the next question. The next question that is given here, use counter example to show that the following statement is false. Use counter example. Now we are looking at counter example. In that, the statement we are being told in this case is that n squared plus 3n plus 1 is prime for all n members of natural numbers. Natural numbers are counting numbers, which we start 1, 2, 3, 4, 5, and so on. Now, is this true? Is this really true? If you try n, they are saying this one is prime. If you try with 1, you are going to say, when n is equals to 1, what are we going to have? If n is 1, what are we going to have? We are going to have 1 squared plus 3 times 1 plus 1. So this is going to be equals to 5, which is prime. Yes, it works. But we want a counter example. An example whereby this particular expression is going to fail and it's not going to become, it's not going to be a prime number. And that's when you'll try, and that's when n is equals to 6. When n is equals to 6, you realize you are going to have 6 squared plus 3 times 6 plus 1. This is going to be 36 plus 18 then plus 1. If you work out this, you are going to get the answer is equals to 55. And 55 can be written as 5 times 11. 55 is not a prime number. Then we can be able to say, hence, this statement that they are saying that it's a prime, this expression is a prime for all natural numbers, for all numbers n, which are members of natural numbers, are prime, then this part has indicated that this expression does not hold for 6. So meaning this expression is not always true for n member of natural numbers to be prime. So when you are going to be asked about counter example, try to find a number you substitute and the expression does not hold, and then in that way we can be able to say we have proven by counter example. This is Roman 1. Then let's have Roman 2 here. And Roman 2 question, it was saying use algebra to prove by exhaustion that n squared minus 2 is not a multiple of 4, where n is a natural number. Natural numbers we have said, 1, 2, 3, 4, 5. Those are natural numbers, right? And so on. Those are natural numbers. But when we are talking about natural numbers, guys, you have to agree with me that natural numbers are even or odd numbers. So if we are saying that this expression, which is n squared minus 2, is not a multiple of 4, we are going to try this expression for both even numbers and for both even numbers and natural number and odd numbers. So we are going to say let n be equals to, let n is equals to 2k plus 1. 2k plus 1. This is an odd number. This is an odd number. So we want to check, is this odd number really a multiple of 4 or not? Let's try out. So we're going to say k, 2k plus 1, you raise to power 2 minus 2. If you expand this, so we are trying for what? Odd, right? If we expand this, we are going to have, we said the shortcut to expand this expression, you will have, you square the first term, 2k, 4k squared, plus the middle term will be 2k times 1 times 2. That's going to be 4k. Then you square the last term here, and that is going to be plus 1. Then we shall subtract 2. So we have 4x squared plus 4k minus 1. And with this expression that we have gotten here, you can agree with me, we can be able, if we divide by 4, all true. Yeah, if we divide by 4, all true, because we are trying to show, is it it's not divisible by 4. That's what we want to show. It's not divisible by 4. Yes, it's not a multiple of 4. If it's a multiple of 4, meaning if you divide the expression you have by 4, you will get a whole number. We are showing that this is not a multiple of 4. So if we divide all terms by 4, we have this first term divided by 4, that is going to be k squared. This term divided by 4, this is going to be k. This term divided by 4 is going to be minus 1 over 4, which is not a whole number. So that means, what does that mean? It means 4k squared plus 4k minus 2 is not a multiple of 4. And we have shown for odd numbers. That's what we have done here for odd numbers. Now let's go ahead and try to show that for even numbers. Yeah, for even numbers. Sure. Let's show that for even numbers. Now, for even numbers, we are going to let 2n equals to 2k, just 2k, not anything else, because 2k is an even number. Let me just write it. Let n be equals to 2k. 2k is an even number. Then we substitute it into the expression that we are given. We shall have 2k squared minus 2. This is going to be 4k squared minus 2. And if we divide all terms by 4, we have, if you divide all terms here by 4, what are we going to have? We are going to have k squared minus 1 over 2, which is not a whole number. So 4k squared minus 2 is not a multiple of 4, or is not divisible by 4. Hence, so since this was even and this was odd, and we have shown in both cases they are not multiples of 4, then we can say therefore n squared minus 2 is not a multiple of 4. Or n members of natural numbers. For all n members of natural numbers. Basically, that's what you are going to do in this particular question, guys. And if you are new to Proflan YouTube channel, consider subscribing so that anytime I'm going to upload more tutorials, you'll be notified. In Proflan YouTube channel, I do maths and physics. So if you are new here, guys, show your support to Proflan by going straight and subscribing, and also checking our Patreon page so that you can be able to download this particular paper I'm sharing here, and also the solutions that I'm working on this given point. So guys, let's dive in, continue with the next part of the question here. And we are told that yes, given that n is a member of natural numbers, prove by exhaustion it's not divisible by 4. That is exactly what we have done in this in the previous question. It's not a multiple of 4. It's the same approach you are going to use in this particular question, because what you are going to do, guys, in order to show this, you are going to prove by exhaustion. Yeah, you are going to prove by exhaustion, both showing that is not divisible by 4 when n is an even number, and when n is not, is an odd number. So this is what we're going to do. Prove that n squared plus 2 is not divisible by 4. We are proving that for n members of what? Natural numbers. And we have agreed natural numbers, they are either odd numbers, these are odd numbers, or these are what? Even numbers. And natural numbers can either be odd numbers or even numbers. So for you to exhaustively prove that, you must show that this is not divisible when n is an odd number. It's not also divisible when n is an odd number. So we are going to start with n is equals to 2k plus 1. This is a case whereby we have our number odd. Then we're going to say this is going to be 2k plus 1 squared, then plus 2. Then we are going to expand this expression. So if you expand this, this squared is going to be 4k squared. Then 2k times 1 will be 2k times 2, that will be 4k. Then 1 squared will be 1, and then we shall say plus 2. So if you put the like terms together here, you are going to have 4k squared plus 4k plus 3. Guys, with this we are going to say that this expression here, it can be written as 4 into k squared plus k then plus 3. So this expression is 3 more. This expression, so we can conclude here, is 3 more than a multiple of 4. So it's not divisible by 4. So this expression, we have confirmed that this expression here is not divisible by 4 because it's 3 more than the multiple 4. Now we are going also to say when n is equals to 2k. Now this is what? A case whereby n is even. Also we want to show that also it's not divisible by 4. And what's that mean? That is going to mean that its expression is n squared. So we are going to say 2k squared plus 2. This is going to be 4k squared plus 2. And we can be able to write this as 4. Yeah, you can see it's 4k squared plus 2. So this one here is 2 more than a multiple of 4. So it's not divisible by 4. So we have shown that it's not divisible when n is an even number, and it's not divisible when n is an odd number. So since these two conditions hold, we can be able to say therefore we have to conclude that it has been shown that this is how you end you cannot just stop here and say that this is now correct. You have to write the conclusion. These are proofs. You have to conclude. It has been shown that n squared plus 2 is not divisible by 4 for both odd and even. Hence it's not divisible for all n members of what? Natural numbers. For all n member of natural numbers. Guys, that is exactly what you are going to do when you are proving by exhaustion. Prove by exhaustion. And next number. Next question. Next question. What does it say, guys? Let's see. Next question. Next question. Next question. Next question is here. Very interesting question. Use algebra. Going to see question like this also. Use algebra to prove that for all values of x. Use algebra. Now this is what? Using algebra. Using algebra. So for all real values of x, for all values of x, x minus 4 squared is greater than or equal to 2x minus 9. That's exactly what we are going to show. So in such kind of questions, you're going to realize that you have to really be very, very careful. You have to be very, 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 very careful when you are handling that. So how are we going to go about that? Because you are having this, guys, you are going to expand. You are going to expand this, and this is going to be x squared minus 8x plus 16 is greater than or equals to 2x minus 9. I take everything on the other side of the equal sign. I'll have x squared minus 8x minus 2x plus 16 plus 9 is greater than or equals to 0. Then if I put the like terms together, I'll have x squared minus 10x plus 25 is greater than or equals to 0. Then if you factorize this, you are going to realize that you are going to have x into x minus 5 into x minus 5 is greater than 0 if you factorize this. So that means that upon factorizing that, what are you going to have? You are going to have x minus 5 into x minus 5 is greater than what? 0. So that means x minus 5 squared is greater than 0. And indeed that is true. It's true that all squared numbers will be greater than 0. So we are going to say all squares of numbers are greater or equal to 0. Yes. Hence, x minus 4 squared is greater than or equals to 2x minus 9 for all x, such that x is a member of real numbers. X is a member of real numbers. So basically, this kind of equations whereby you are supposed to be proving this way, you are going to have your argument that way. Yeah, so let's look at the next question. Question number 5. Show the following statement is untrue. This Roman 2, this was Roman 1, Roman 2, and Roman 2 is saying show that the statement is untrue, and the statement is 2n plus 1, 2 power n plus 1 is prime for n all values. For all values, n is member of natural numbers. So we show that it's untrue. this question is basically counter example. You need to come up, you need to have actually one value which is going to prove that it's not true. Then that is going to show indeed that this kind of question is not going to work. So my expression I'll use in this case is when n is equals to 5. You can try other values, but we are going to say so that I can just proceed with the next question. When n is 5, we put it here. It will be 2 power 5 plus 1. This is going to be 2 power 5 is basically 32, right? 32 plus 1, it will be 33, which is equals to 3 times 11, not prime. So 2n plus 1 is untrue. Is untrue. That's a lie. Whoever who tried to trick us, we have proven that indeed that's not true. That's not true. Yeah, that's not true. Yeah. Right, guys, I believe you are getting value from this particular tutorial. So if you are new to Proflan YouTube channel, guys, just subscribe. Huh? Yeah, just subscribe. And all the best for those guys who are going to sit for an exam. For those guys who are going to sit for an exam. Okay, so the next one here is this question we're told, use algebra to prove that 3x plus 1 is greater than or equal to 2 root 3x. Use algebra. Now, using algebra here, we have 3x plus 1 is greater than or equals to 2 root 3x. Now, this kind of expression, guys, you can see indeed what we have is 2 terms on the other side of the equal sign. So you are going to square both sides. Square both sides. So if you square both sides, you're going to have 3x plus 1 squared is greater than or equals to 2 root 3x also squared. So guys, if you square this, what are you going to have? What are you going to have here? You will have 9x squared plus 6x plus 1 is greater than or equals to, and this is going to be 12x. Then if you put this on one side, you should have 9x squared plus 6x minus 12x. Then we have plus 1, right? And that is going to be greater than what? 0. So 9x squared minus 6x plus 1 is greater than 0 can be written as, we can be able to factorize this. And if we factorize this, we are going to have 3x minus 1 squared, which is greater than what? 0. You can see this one is similar to the other question that we did. And anytime this is greater than 0, we are going to say, so for all square numbers, or we can say all square numbers are always greater than 0, isn't it? So for all x greater than 0, because that condition basically was given here, x greater than 0, then 3x plus 1 is greater than or equal to 2 root 3x. from this particular condition. Okay, so that is how we are going to stop on that question. Next question. Show that the following statement is not true. This was Roman 1. And then we have Roman 2. We are showing that it's not true. If we are showing that it's not true, we need a counter example. Show that the following statement is not true. Sum of 3 consecutive prime numbers. Sum of 3 consecutive prime numbers is always a multiple of 5. Sum of consecutive 3 prime numbers is a multiple of 5. Is that statement true? Or was it just working for a few numbers? So look at, for instance, 5 plus 7 plus 11, it's 23, which is prime. Okay, it's fine, it's prime. Yeah, it's prime. But is this a multiple of 5? Is it yes, it's prime. Yeah. Show that the following is not true. The sum of 3 consecutive prime numbers is always a multiple of 5. Yes, we have chosen 5, 7, 11. These are 3 consecutive prime numbers. It's 23. Is this a multiple of 5? Not a multiple of 5. So the statement here is false. We have shown that it's not true by just giving an example there.